Okay. Is it possible to hear me? Okay, very good.
Hello, hi Wolfgang.
Hello, Alexei.
Yes, how are you?
Fine, and you?
Yes, fine, okay.
Very
well,
good.
So we start in a couple of minutes.
Yes. So is the first speaker, Nuno Almeida is there. Okay. Yeah. Hello. Hello.
Hello.
Hi. Okay. So you are ready for the first.
Yes. Yes.
Okay. So is it possible for you to share the screen? I think it should be possible. So I think I don't need to do anything. So just try it.
Yeah. Okay.
Ah, very good. Okay, so then we can start probably, Alexei, because there will be other sessions later, or not?
Yes, indeed, we have two parallel sessions, and they are synchronized in time, so you can move from one room to another.
Okay, so we need to have a good discipline. Yeah, so then welcome from my side for this SPECOM session 7, multimodal analysis and synthesis in room 2. So we have 1, 2, 3, 4, 5, 6 presentation, 20 minutes each is the slot for each presentation, and we have 15 minutes presentation time and 5 minutes questions. Yeah, 5 minutes for questions and answers, 20 minutes in total. And I think the easiest way would be to raise, for those who would like to ask a question, to raise the hand in the room, and then so I think the moderator will unmute, as far as I understood. So, but we will see. Okay, so the first paper, designing and deploying an interaction modality for articulatory-based AVS, presented obviously by Nuno Almeida, the first author, and co-authors Diogo Cunha, Samuel Silva, Antonio Teixeira. I don't know whether I spelled them, I pronounced everything correctly.
It's
okay. More or less.
Yeah.
Okay, Nuno, please go ahead and start.
So my name is Nuno Almeida from University of Aveiro, and I will present a new audiovisual speech modality based on the articulation of the vocal tract. So to start, it is important to understand that we humans communicate with each other through speech mainly. But in human-machine interactions, speech communications still poses several challenges. Although technology is evolving in this field, the speech technology, in this field of speech technology and the digital assistants. But the current products that we have mostly rely on the auditory signal of speech. But visual features of the speech could provide additional cues that can result in a greater resilience of speech communications. So most approaches of audiovisual speech rely on machine learning, the creation of models, but those works like a black boxes, and we don't know how it really works. Technology is evolving in this area, but our knowledge in the real way how speech, audiovisual speech production is done, we don't have very knowledge about that. So we need a different approach to the synthesis of this kind of speech to better understand how the human processes the speech articulation. And how it relates to the visual cues. This also enables a more refined control and analysis of the system parameters. So this kind of systems poses several challenges. It relies typically on complex technologies. It is needed knowledge of 3D modeling in order to design an avatar. Other important aspect is that we need to synthesize the speech, and we need to synchronize the speech with the lips and the mouth. Finally, after having a functional prototype of such systems, we need to have an easy way to adopt them in other systems. So this work is the evolution of a previous work from our team, already published in Biosignals. That work already envisions a conceptual framework for the development of an articulatory audiovisual speech system. It is composed of the three main modules: the core that should constitute the central element of the framework that deals with the actual production of audiovisual speech output. The second relevant aspect is the interaction modality. So we need an easy way to deploy the modality and that to be easy to adopt in other systems. And finally, a module to evaluate and validate the outcomes of the produced audiovisual speech. So in the previous approach, we have this architecture that relies mainly on in the core, the task dynamics applications, the TADA, responsible for computing the trajectories of the different vocal tracts articulators. The lips trajectories are then used to modify a realistic avatar, which will be rendered with the audio. Here, the system relies on two services: the articulation and the syllabification service. In the previous versions, this module was limited, so we tried to improve also the core of our audiovisual speech synthesis system, and and we have updated the syllabification service. To do this, we used machine learning to convert the graphemes to phonemes. In the previous work, we have a dictionary, so it was very limited in terms of supported words. So we used two different models, one to convert graphemes to phonemes, and then to make the syllabification representation for the TADA system. The table shows a simple example of the conversions that are made. So here we have the network that we use, the bidirectional short-term memory. It was proposed by Google, I think, the GEP2P, and used the project Natura dataset. This allows that to have lower wrong prediction in the conversions of our words or sentences to the syllabification. and that's our evolution to the core. To understand why we need the modality, we have a simple illustrative scenario, which is on a smartphone, where users can interact with a smartphone devices installed in the house, and they can use multiple modalities such as speech and text. The audiovisual speech modality could be used in the person's tablets, for instance, to render the talking avatar, or while the person is in the living room, for instance, the avatar could appear on a display or a TV. So we have found several requirements to our modality. So our modality should be decoupled from the entire system, so it would be easy to exchange modalities or upgrade the modalities and just exchange it in the system. It should be designed according to standards, so it could be easy to be adopted in several systems. One of the main goals is also its accessibility in multiple devices and operating systems. Our modality is composed by audio and visual, so we will have as a requirement for those to be rendered in different devices, or possible to be rendered in different devices. And since this needs several heavy computational work, this work should not be done in these devices, mainly because they don't have much processing power. So in previous work of our team, we have proposed also a multimodal architecture. It is easy to deploy and adopt by applications. And in the central of our architecture, we have the interaction manager that is responsible for the communication of all the modules and modalities. So in this work, we have created the modality, and this is an overview of the system we have created to test it. So we have in red the stream viewer, the output modality, which is the interface for the user of the avatar modality, and it relies on a part of the modality that is installed on a server. This modality uses the core services of the audiovisual speech, and it communicates through the interaction manager. There's a simple text input modality that is just to send the message to be converted to the speech synthesis and show it in the stream viewer. So here we have the screenshots of the avatars. On the top, there's the text input modality, is just a text box and a button to send the message. And the avatar modality is our realistic avatar, that is the face of a colleague of ours. So in this work, we have evolved the previous system that was limited by the amount of words that it could support. Now we can convert any word and the avatar will read it. And we have created a modality based on a photorealistic avatar that is easy to integrate in new applications. So in the future, this modality can evolve, and the modality that already use it is just to exchange this modality. So thank you for your attention, and it's all. Any questions?
Yeah. Nuno, thank you very much for a nice presentation. So are there other questions from the audience? Okay. Okay, during the time that you're preparing questions, perhaps I may ask you a question. So in your slide, I've seen you have a user and a context model in your architecture.
Yeah.
So what is contained in the user and context model? What information? Yeah. So what is in there, and how do you acquire it? Yeah.
Okay. Our team have been working in this architecture a long time, and in the one of our works, we have designed the architecture, and we have as our context a smart home. So in our home, we have sensors that will feed the context model. And also we have the user model, which the user can configure. And for instance, if the output modality says that he needs the audio to be more loud, for that user, the audio will be louder.
Okay. So if I'm a regular user that uses the system a long time or regularly,
yeah,
then it will adapt to my habit.
That's why the models are there. So if, for instance, we have context, and in the context we have the brightness of the room, also the brightness of the display could be adapted if it was darker or lighter in the
okay. And another question. So I've seen that it is in. So it is it designed for a specific language, your system, or can we use any language? Is it possible to use it in any language?
Okay, our approach is for Portuguese, European Portuguese.
Yeah. Okay. Yeah, I've seen. Yeah, but
and because of we use models, we need to create models for other languages to.
Okay. Okay. So it's
in terms of the second part of the work, the modality, if the core works with other languages, it would be easy for us to support other languages.
Okay. So it's very flexible. Yeah. Okay. Thank you very much. So are there more questions from the audience? So we have 14 participants. Is there someone having a question to Nuno? No? Okay. So then thank you again for the nice presentation, Nuno. And I think we can already move to the next talk.
Thank you.
So Abner Hernandez, are you there?
Yes. Can you hear me?
Okay. So could you try to share your presentation slides?
Yes. Okay.
Okay. So then I will introduce you and your colleague, Multimodal Corpus Analysis of Autoblog 2020, lecture videos in machine learning from Abner Hernandez, who is the presenter, obviously, and Sung-Hee Yang, his colleague, and both are from Germany. Yeah, so please.
Yeah,
Abner,
thank you.
Let's start. Yeah.
All right, yeah, so I'm Abner Hernandez, and I'm a researcher at the Pattern Recognition Lab in Friedrich Alexander University, Erlangen-Nuremberg, and this was research done with my colleague Sung-Hee Yang. And so today I'll be introducing our project, which is the development of a corpus of lecture videos and specifically for video to blog conversion. So we named it Autoblog. So the motivation of this study was based on the fact that we've seen a recent increase in video lectures at our university. And I'm sure this is the case with other universities as well. And so we thought with this major increase in videos, we need some tools to process these lecture videos to be beneficial for students. So for example, at our universities, if we look at the number of videos being uploaded at our video portal website, which is a website specifically for professors to upload their lectures, between the years of 2017 to 2019, we saw around 500 to 700 videos being uploaded during the summer semester. However, once we hit 2020, 2021, we see a major increase where the videos being uploaded are above 5,000 videos. So the main goal of this study is basically to try to start developing a corpus for the purpose of lecture video processing. And in our case specifically, we were looking at a corpus to convert video lectures into blog format for kind of supplementary material for students. And this came about as students who were viewing our lectures online with online learning these days, they were requesting some more sources to supplement their study aside from just looking at the videos. And so this involves quite a wide range of tasks to do this goal. So it involves, of course, automatic speech recognition, keyword extraction, lecture summarization, and there's many more other tasks that could be done with lecture videos that can be used in the educational field. So yeah, as I mentioned, our goal is to take a lecture video. For example, in this case, we have a video from our pattern recognition lecture on classification, and this was uploaded on YouTube. And then our goal was to have a system that can take that video and generate a blog-like version so that after watching the video, or if students were unable to attend class or watch the videos, they can go to this blog version of the same video and review what was discussed during the lecture. Automatic speech recognition for lecture videos have been studied for quite a while. One of the earlier studies was done at MIT with their computer science lectures in 2005 by Park and al. And others. So basically they were testing how to improve the transcription accuracy of computer science lectures. And they found that, increasing the amount of relevant training material, such as material from textbooks, was more beneficial than just increasing, say, language models on general data that's available. And a similar finding was done or found with Japanese lectures, where they looked at the importance of language modeling. And in this case, they included information on the syllabus of the course and compared it to just a corpus of general presentation, political or other material, and found that, yeah, of course, the material that's more relevant to the lecture or more academic related material is more important. And similarly, there's the TEDLium dataset, which is a lecture-like corpus, but in this case, there was only audio data available, whereas we want to look at lectures in a kind of multimodal perspective, looking at the image or the video as well as with the audio data. And so these studies basically have shown the importance of adapting acoustic or language models to contain information, not just huge amount of data, but including information that's relevant, such as academic-based material. for keyword spotting, which is useful to find the relevant keywords for studying. They can also be done in a multimodal perspective. So in earlier studies, they looked at audio signal along with ASR transcriptions or PDF slides. So this can be looked at through prosodic information such as pitch, duration, or energy with the audio signal, or you could look at lexical information using different statistical algorithms or looking at part of speech. And in a recent study, they also found that the text content from video frames using OCR was actually more beneficial than just using the transcripts of ASR, but this turned out to be only the case when the transcripts had errors or were not manually corrected. In that case, it's the transcripts that perform better. But this just shows that looking at lecture information requires a multimodal perspective. And similar with summarization, we have studies looking at handwriting extraction using histograms of video frames to cut for important segments in the video, looking at video skimming generation using shot boundary detection along with histogram information, and also looking at image and text-based methods for summarization. And there have been some studies showing that, at least with Shimada and others from 2017, that the summarized slides, students who previewed the summarized slides achieved better scores compared to just looking at the full slide themselves. And so our corpus currently, it contains 4 full semester lectures. So we have pattern recognition, deep learning, speech and language understanding, and medical engineering. And these range from between 11 to 14, 15 hours. But for the purpose of this study and this analysis, we only looked at the pattern recognition courses or lectures. So in this course, we had 43 videos with about 11.5 hours. We also have unedited videos, as this course for this course we used pre-recorded videos and had students watch the videos then. And yeah, we also have manually corrected ASR transcripts. So for us, we uploaded the videos on YouTube and just took the automatic captioning systems and then had students manually correct the output of the ASR. And we also have lectured slides in PDF format, of course. So for now, the data set is quite limited in the range of lecture styles. Right now, what we have is a format where the lecture material or content is on the left side and speaker is on the right side. But in the future, we plan to include other formats such as, say, Zoom type lecture videos where the speaker is on the right, top right, or other locations in the video. Yeah, so that's just a sample of that. One issue that we have to take into consideration is that since a lot of our lectures are based on machine learning, we have a lot of mathematical notation that we have to consider. So initially, with the YouTube ASR transcript output, we had students manually correct the output and then standardize the math notation so that when we evaluate the ASR, we have the kind of written out words of the notation. But we also wanted to keep the math notation with all the symbols and everything, since in the future we would like to look at building models where we can train a network that retains the mathematical notation or contains the symbols in the vocabulary, so that when we train the system, we don't have to do this post-processing where we convert the words into symbols, at least when we upload the content to blogs. So for now, we've only been looking at the YouTube's automatic captioning system, since we've noticed it performs very, very well, at least with English. And even though the professor in the pattern recognition course had a German accent, the word error rate of the videos, the average word error rate was quite good. It was around 6.25%. And between the 43 videos, it ranged from 2.65% to 15.73. And you can see that there were some mistakes, mostly related to math-based connotation or with nouns. But we think it's a useful tool for professors or teachers who want to obtain captioning but aren't able to use any ASR-based system. Next, when we convert the when we have the output of the YouTube ASR transcript, it's just a large number or a file of just the transcripts in general. We don't have a nice kind of segmented format as we would like to see with periods, full stops, and punctuation, which can be remedied by using tools like Grammarly, which can kind of correct some grammar. However, without any notification of segmented sentences, it doesn't perform as well. So we wanted to also have a tool that can take the YouTube ASR output or transcript and convert it into segmented sentences. And so we had this model, which was an LSTM using conditional random fields, where the output kind of computed probabilities of tokenized labels, where the label would denote whether the word was at a sentence boundary or not. So initially we took around 1 million sentences from the Tatueba dataset of English sentences and just trained a model on that. And just using that outside data, you can see from the base model that the F1 score is not too good. It's just above 50%, which is okay. But later we fine-tuned the model with an extra 7,000 sentences based on the material of the same professor, but in a different course. And you can see that there's much higher improvements in the F1 score. And here are some sample sentences of the segmenter. So I picked a good sample, which obviously is not the case all the time, but you can see with the manual segmentation that was done by a student compared to the output of the model segmentation, that in general, it's able to capture what we would see, or it's able to segment as a student would. There was only few mistakes. So in this example, it didn't segment the sentence beginning with "if you're interested," and that likely makes sense, as it's probably more common to see "if" being in a sentence, within a sentence, not beginning of a sentence. But it's showing some positive results. And so we use these segmented sentences when we post to our blog. And then lastly, we just looked at some keyword extraction techniques. So with our ASR transcript, we wanted to have some keywords so students can look at the main words or keywords that should be focused on when studying. And so we used the Uyake approach, which was a recent statistical approach developed about last year. And we can see that depending on the course lecture, so kernel PCA, Laplacian SVM, you kind of get the keywords of what you would expect. So in conclusion, we try to introduce a corpus specifically for lecture video processing and specifically for the development of a video to blog system. We evaluated the YouTube's automatic captioning system, which ended up having a word error rate average of around 6.25% between 43 videos. Second, we evaluated the utility of having a model trained to predict sentence segmentations based on the ASR outputs, and found that A base model was only able to achieve around 50% accuracy or F1 score, whereas a fine-tuned model can achieve up to an 80%. And then we also extracted keywords using the Yake algorithm to see how well it would perform with academic based material, and the resulting output is what we expected. So this is a very, very, very initial work, and there's a lot of things that we still need to do. So one thing is to develop an in-house speech recognizer trained specifically on university lectures. So we don't want to be dependent on YouTube's automatic captioning system. So we're looking into Caldi, ESPNet, Wave2Vec, SpeechBrain, and other toolkits to see what can be the most convenient for developing this kind of system. We also want to improve the math and punctuation recognition. So right now with, say, YouTube's automatic captioning system or most other ASR systems, the output is just a plain transcription without any punctuation or spelled out mathematics. And we want to try to train a recognizer that can maybe detect that so we don't have to rely on post-processing. Next, we're looking into a slide transition detection tool. So we currently have a paper under review using CNNs to detect slide transitions. And this is to be used to get the timestamps of when the lecturer switches slides, so that when we can kind of align what the ASR output has outputted with the correct slide. So the order of how it is in the blog can be a bit more clean. And we didn't look at lecture summarization yet, but we plan on doing that along with spoken keyword extraction. So comparing how the text-based keyword extraction is to the spoken keyword. And of course, we also want to increase our data set. Currently, we only have about 2 speakers in the data set, and we're limited to topics within the computer science department, but we want to also see if other professors within our university are open to providing their data. And that's it. Thank you for your time.
Yeah, Abner, thank you very much for the nice presentation, and we are perfectly on time. So are there questions from the audience?
I have a question, if I can.
Yes, Ivan, hello. How are you?
Hi. I'm fine. What about you? Anyway, thank you for your presentation. It was very interesting. I would like just ask about your corpus, if it will be or if already is publicly available.
Right now, just the videos themselves are available on YouTube, but we plan on releasing kind of a more packaged corpus where we have the transcriptions, the alignments, and kind of a more organized corpus. So right now, we're not. Right now, we have basically one course semester where it's kind of nicely organized, but we're trying to include all the other stuff before we release it publicly.
Okay, thank you.
No problem.
Okay, thank you, Ivan. Are there more questions? So Abner, I have a question. So do you think that keyword spotting only will be sufficient to deal with this content extraction? Because I assume that it's too simple, or the lectures are too complicated. So don't you need NLU, for example, or performance?
Just for in what context?
Yeah, okay. So do you just want to extract the topic and that's it? No content, no more detailed content.
I think it's more for in our portal website. We want to have, yeah, I guess just the keywords might not be giving much information about the actual lecture, as the lecture can be very complex, but yes. I think the keywords just is more of a guide for other students to, if they're looking at a, say, catalog of our lectures, just to see what this lecture, what the topics are covered.
Okay.
I see. It's not meant for a more deeper,
for more sophisticated processing. I see.
Yeah.
Okay, and this is your PhD or your PhD work, part of your PhD work?
We'll see.
We will see. Okay, very good.
We're in the first year, so.
You're in the first year, okay. Yeah, then good luck to you. Okay. So Ivan, are you the next one by chance?
Yeah, I guess so.
You are? Okay, so Ivan, can you try to share your, oh yeah, okay, everything works perfect.
Okay, perfect, great.
So actually, I know all the authors of the next paper, Ivan, Gruber, Marek Skus, I don't know, Milos Chelny and Alexei Karpov. So it's obviously a cooperation paper between ITMO and the University of Pilsen.
Yeah, it's correct, and also Spiras, because Alexei is working.
Yeah, of course. Oh, Alexei, I'm sorry. Okay, X-Bridge, image-to-image translation with reconstruction capabilities. Okay.
Okay. Anyway.
So go ahead.
Okay, so I will start about our paper. Firstly, I would like to briefly talk about main contributions of our paper. We presented a novel supervised approach for image-to-image translation called X-Bridge, and we demonstrated the power of this new approach on hard facial image-to-sketch translation task. We also reached qualitative and quantitative results which overcome other tested state-of-the-art methods. Now for problem definition and briefly about motivation. So we can define image-to-image translation as a translation of image from the first domain to the second domain while preserving important image attributes. And in real world scenarios, this is the case, for example, in attribute transfer, in painting, style transfer, super resolution, or heterogeneous image recognition. Nowadays, the most popular methods are based on generative adversarial networks, which is also the case of our proposed approach. And now already for X-Bridge method, as it was already mentioned, it's based on generative adversarial networks. It's supervised methods. It's supervised method, and it's composed of 5 main parts: 1 encoder, 2 generators, and 2 discriminators. These 5 parts can be divided into 2 main paths. I will talk about these paths in more detail later. And the first path is a translation, and second path is reconstruction path. Each path can be imagined as separated generative adversarial network. Our method also work with a shared latent space assumption, which means that we assume that corresponding images from 2 different domains can be mapped to the same latent code. Now, at the right, you have a simple scheme of our method. The input into the method is an image from the first domain. It is processed by encoder E, which's goal is to encode the input image into the latent space Z. And then we have here 2 main paths. First path is translation path with G1 and D1, and second path is reconstruction path with G2 and D2. The goal of G1, which is generator, is to generate image from the latent code provided by encoder, and this image should be from the second domain. The goal of generator 2 is to generate image from the first domain based on the same latent code as generator 1. And then we have standard discriminators as in all all standard generative adversarial networks, which goal is to distinguish between real images and fake images. It should be noted that discriminator 1 is also conditional discriminator, which means that at the input of the discriminator 1 is also the original image from the first domain. So, the goal of the generators is to generate as real and as precise image as possible. And the goal of discriminators is to distinguish between these images and real images. So now for the experiments. We utilized a CUFSF dataset, which contains 1,194 images from FAIR database. And for each of them, this dataset provides sketch drawn by an artist. All the images are captured from frontal pose in controlled lighting and with neutral expression. As for the training setup, we convert all the images into grayscale and resize them to resolution of 256.256 pixels. Moreover, we normalize all of them between 0 and 1. We take the whole data set and split it into 3 subsets: train subset, validation subset, and test subset. Whereas train subset contains 80% of data, and validation and test subsets contains both 10% of data. Our method was trained during 150 epochs with mini batch size equal 1 using Adam optimizer. And we tested 2 main tasks: image to sketch translation and sketch to image translation. We compare our method with 2 methods, Pix2Pix and Munit, whereas Pix2Pix is supervised method and Munit unsupervised. And now some exemplary results. Here you can see some results from real image to sketch translation. We argue that Munit, which is unsupervised method, provided the worst results because they were generally blurry, and the quality of images from Pix2Pix and our XBridge was much better. When we try to translate the images other way around, the Munit method once again provides blurry results, but overall the quality of the results were much lower than in the first task, because we argue that this task is much harder for the network than real image to sketch translation. In the third experiment, we compare generalization capabilities and robustness of the method. In the first row, you can see how the methods dealt with translation of glasses. As you can see, Pix2Pix completely failed to convert to translate image with glasses, whereas the other 2 methods more or less translate these glasses correctly. In the second row, you can see how the methods dealt with rotation. Once again, Pix2Pix provided arguably worst results in this task, because it has a really hard time to understand that, for example, here the right eye should be occluded and shouldn't be there. So Pix2Pix model the right eye there anyway. And now for some quantitative results. To obtain quantitative results, we take the whole testing set and we transfer it from the sketch domain to image modality. We extracted features from this transferred set and also from the corresponding original real images. And after that, we calculate the similarity of extracted features. In idle case, the images should be totally the same, and we should get results equal to 1. However, as you can see in the table on the bottom, we are not there yet. Yeah, but our method XBridge overperformed other tested methods. It should be noted that as a feature extractor, we utilized pre-trained arc face model, and yeah, that's it. And so to conclude, we presented a novel supervised method, which outperformed other tested methods in qualitative and also in quantitative results. We also argue that XBridge improves robustness and generalization capacity. And for our future research, we would like to focus on unsupervised image-to-image translation, because as you can imagine, sometimes it's really hard to obtain annotated data for some modalities, and sometimes it's also very expensive to get annotations for these data. That's all from me. Thank you very much for your attention. And if you have any questions, feel free to ask.
Okay, thank you very much, Ivan, for the nice presentation. So, Ivan, I have directly a question. So the samples you have shown us are all very clean images with the faces very clean in front of the camera, but of course, this is not the reality.
Yeah.
So how does it work, or how does your approach perform in case of real life situations?
Not very good, to be completely honest. But I believe that if we get a more annotated data from real world conditions, it can work. But right now, for the training, we had only these image pairs, so it's really hard for the network to deal with conditions which it never seen before.
Okay. Yeah.
So yeah, so that's also the reason why we would like to focus on unsupervised unsupervised learning, because then there will be much easier to obtain these data in various conditions.
Okay, I see. And another question: are you the only one working in this area? Because I can imagine that other research groups are also working in this area. And in this case, how do your results compare to others?
Well, I'm not really the only one. Actually, in last, I guess, 10 months, there were many interesting publication in this area, and they all just improved state of the art. So to be completely honest, this is not the state of the art anymore right now.
Okay.
But
I'm asking the good questions, obviously.
Yeah. That's fine. We can be honest with each other. So, but but you know, I still believe it's interesting work for others. So
okay.
so, and we also on the other hand, we also have a GitHub repository free available for everyone, which is not the case for the new work. So.
Okay. Yeah. Okay. Very good. Yeah. So are there other more questions from the audience? I'm just looking in my board here. No, not really. Yeah. Okay. So then we can basically continue. So I see again Ivan.
But I am not presenter anymore.
You are not the presenter, okay?
No.
But there are many other names. So who is then the presenter? Just to make it easier for me.
Tomáš Zitka.
Tomáš, okay. You are Tomáš, okay. Hello. So, okay. Tomáš, can you try to share your?
Yeah, sure. I'm right on it. And is it working?
Yes, very good.
Oh,
okay. And this is Pilsen only work.
Yes.
Okay, so OCR improvements for images of multi-page historical documents. Very interesting. So I think even though we are a little bit ahead of the schedule, I think we can start. Let's start, okay?
Yes, so good afternoon. My name is Tomáš Zitka, and I will present our work in OCR improvements for images of multi-page historical documents. So our work is continued work on a project that was introduced on this conference last year. And this project concerns itself with providing access to historical documents from archives of NKVD, from archives of NKVD in post-Soviet states. And these archives are usually related to history of former Czechoslovakia. That's why we in Pilsen are interested in this problem. And the main issues in this task are poor quality of the documents as well as scans, and multiple languages like Russian, Ukrainian, and Czech in these documents. Our main contributions for this task are a new page segmentation algorithm, which we fine-tuned for our task, the Skewing algorithm, and we also improved OCR performance specifically for processing of these documents. These three algorithms together lead to significant improvement in word recall task, which is very important for us because we want to archive these documents and allow easy search in these. Our results manifest in a pipeline, which processes these documents and creates a database, searchable database, which is available at this website. Here is our processing pipeline. The first step is page segmentation, because in the scanned documents, there are often many pages in one scan. So we need to find the suitable page which we want to process by OCR. But before this processing, we want to apply the page skew algorithm to improve OCR performance. The page segmentation algorithm, in page segmentation algorithm, we face an issue that that currently available algorithms aren't performant enough to provide satisfactory results for our segmentation. So we have to fine-tune our network. We used faster RCNN with ResNet 50 as backbone, and manually annotated 3,000 scans, which resulted in 3,189 pages, which we want to segment. We used training and validation split in these ratios. And we trained on the training set for 10 epochs with batch size 1 and learning rate 1000, which resulted in a mean average precision of 0.993, which is enough for our needs. Here is an example of page segmentation results for scan with 2 main pages. Pages which then continue to other processing. For the skew algorithm, we adapted our previous research. The skew algorithm starts by converting image by fast Fourier transform into spectrum space, and then we iterate over angles with in the specified range with a specified step and sample points on the line with the angle that passes through the center of the image, compute the sums of the sample values, and then find the largest sum. And this largest sum denotes the angle we want to use to deskew the image to rotate it in a opposite angle. To verify that this algorithm works, we used 500 synthetic text documents with rotation information and 50 real-world data for which we don't have this rotation information. For the 500 synthetic text, we tried different angle steps. We tried different angle steps, and we observed that for the smallest step we have smaller error, but we have largest maximal error, which suggests that the smallest step is very sensitive to different noise and such. So we evaluated the middle step 0.25 as the best, because it has still low average error and also lowest maximal error. For 50 real world data, we try to evaluate effect of resizing the image or cropping the image on the accuracy of the rotation or on the rotation. And here we can, in this table, we can see how the different different resizing of the image affects the rotation. So for not resized image, it is basically rotated the same as the original image. And as we subsample the image, the rotation angle changes, and presumably this decreases accuracy. Same for crop value, where this is the percentage of the image that was cropped. As we can see, the subsampling and crop value doesn't affect average error too much, but it significantly decreases processing time. So this shows that our algorithm is robust against both the downsampling and cropping, and it also, the previous table experiment shows that it's sufficiently accurate for our needs on the skewing the scan documents. For optical character recognition, we use Traceroute engine version 4.1.1. However, the base model available online have insufficient performance, mainly due to the fact that our documents are mainly time-written, whereas the Traceroute engine is trained on typeset documents. But our documents are also deteriorated with various paper defects, and also the scans are often of poor quality. So to improve our outsider performance, we decided to fine-tune Traceroute engine. However, we don't have enough real world data to do this effectively, so we also use synthetic data. For synthetic data, we use variational autoencoder, which simulates background texture of the old paper, and then publicly available typewriter fonts like the ones listed in parentheses. And we typeset, and we set these fonts, and we set random Russian text obtained from internet using these fonts over the background texture. And in this image here, we can see results. The top row shows original data or real world data, and we typeset the same text. On the left, we see the raw input from variational autoencoder and then text set over it. And as you can see, the color palette is very different from real world data. So additionally, we use histogram matching with some real world data samples as targets, which results in much closer colors to the real world data in our synthetic data. For retraining Tesseract, we created a set of tools which is available at GitHub. And this set of tools serves for training the Tesseract, computing errors, and generating all the data. So we generated 1,500 full text.
So Tomasz, we cannot hear you anymore.
Training.
Okay, now it's getting back. So we didn't hear the last 15 seconds.
Oh.
Okay, so that was a problem.
Yeah, I heard something and then you spoke.
It's fine, so it's fine.
This slide, should I repeat this slide?
No, the next one, yeah.
Just this one, okay. Yeah. So for Traceroute training, we created a set of tools which is available at this website, at GitHub. And this set of tools contains tools for training the Tesseract and preprocessing the data and computing errors. For training, we created 1,546 full text synthetic pages as I described before. But also we annotated 100 real-world documents from which we extracted 473 single-line real-world inscriptions, which we used for training, and also 161 paragraphs, which we used for testing. As a base model, we used Russian model because our annotated data and data we focused on in this iteration were Russian, and we used Russian model publicly available at Tesseract GitHub as the data as is recommended by Tesseract documentation when you are retraining the Tesseract. We trained for 3,000 iterations using an optimizer with adaptive learning rate starting at 10 to power -4, which is again recommended in Tesseract documentation. Here are the results. For pre-trained, non-fine-tuned model, we have very poor character error rate and word error rate. When we fine-tune on the synthetic data only, we can overfit on this data, but this doesn't improve performance on the real-world test data much. When we train on real-world data, we can improve performance on test data just a little bit, but when we combine these two approaches, we can achieve significant improvement, which actually results in improved word recall in our downstream task. To test our pipeline, we designed an ablation study in which we evaluated word recall. We used 80 testing documents, which were different from those used for fine-tuning Tesseract, and from which we have annotated 6,255 unique words for which we tested the recall. Here are the results. You can see that adding individual steps of the pipeline increases word recall, which culminates in word recall increase of 8%. And when we add also output of the OCR on unprocessed document, we gain almost 20% in word recall. So in conclusion, we tested our pipeline in ablation study and gained improvement of 19% in word recall, which was what we were aiming for. For future work, we intend to segment images into logical blocks, which we hope will help Tesseract OCR engine even more, because one of the main issues of the Tesseract is its segmentation, which is not optimal. And we also want to add document classification into the pipeline to improve archiving. Here are some references. This is the paper we are building on from the previous SPECOM, and the paper that describes our original SQ algorithm. And that'll be all from me. Thank you for your attention. And do you have any questions?
Yeah, thank you very much, Tomasz, for the nice presentation. So are there questions from the audience? Okay, obviously not, but I have two questions, Tomasz. So the first one is probably I didn't get that right or correctly. So why is it necessary for you to use synthetic data? So you were just talking about synthetic data, so I didn't get it. So why is it necessary? What is the point? Yeah, this one.
Yeah, the main problem is that we don't have enough real-world data to actually impactfully fine-tune the Tesseract OCR engine. It requires much more data to be fine-tuned, but there's the synthetic data can be generated. Like we can use the type return fonts. So this is the possibility, basically currently only one available to us to improve performance of the Tesseract.
Okay, yeah, I see. And another one is, so are you bound to the historical documents? Of course, this is very important, but can you use your approach to other type of documents as well?
Well,
because it's very specific type of document, of course, but is it?
Yeah, that's we are specifically targeting these specific documents. As for the pipeline, I guess the individual steps would be definitely meaningful and useful for different kind of documents. But you would have to tailor each to the specific documents, especially the OCR engine and probably the page segmentation. The page SQ algorithm is fairly general, so it could be probably transferred to other tasks.
Okay, I see. Yeah, are there more questions? Otherwise, we would continue and move to the last one. Ivan has a question on his paper. Okay.
Maybe I can add that the Tesseract has really good results for nowadays documents, so you don't have to fine-tune it. But the problem of its poor performance is solely only for these historical documents. So the processing pipeline is okay for any document, I guess, but yeah, we need to take some additional steps to make it work for historical documents.
And also the evaluation results, I mean, there was still a quite high error rate.
Yeah,
So,
yeah,
but I did want to ask this question, not to seem to be impolite, but
yeah, but because the documents are kind of mess, to be honest.
yeah, okay.
Yeah, in origin, I don't know if Tomáš has some image of the documents in his presentation.
There is the one with the segmentation.
Yeah,
This is the nicer one.
This is the nicer one. Sometimes
Okay,
there
okay,
are
I
some
see.
you know many pages randomly over each other, and yeah, it's kind of hard problem.
Okay. So then these 60% were already still a good result.
Yeah.
Even the application behind. Okay, very good.
Mhm.
Okay, yeah, very interesting, of course. Yeah. Okay, so then I see Dibadata dash.
Yes, I'm here.
Ah, you are here. Okay, hello.
Hi.
So,
Let me share my screen.
so you have the last paper.
Yes.
Okay, imagined, intended, and spoken speech envelope synthesis from neuromagnetic signals. Oh my God, this sounds very interesting. I've never heard about this.
Yeah. Thank you for this opportunity, and hello everyone. My research is a little bit different than the previous talk, so but I promise you are not going to get bored. So yeah, I'm Devadatta Das. I'm a final year PhD candidate at the University of Texas at Austin. This is one of our research work which essentially tries to decode speech information from the brain using the magnetic signals of the brain. And why do we need to do that? The motivation is for the patients like Dr. Stephen Hawking. They are suffering from like amyotrophic lateral sclerosis, a motor neuron disease, which eventually leads the patients to a state called locked-in syndrome, where the patients are completely paralyzed but cognitively aware. So since their articulators are paralyzed, they are not able to communicate. But it is very essential to restore their communication ability that can prolong their lifespan as well. But the only way we can reestablish their communication is via the brain. So a very common approach to this problem is brain-computer interfaces that people have been working a lot. You must have heard EEG or electroencephalography-based brain-computer interface payloads, where the patients would basically focus on a screen where there would be different letters and numbers, and they would focus their attention on a particular letter, and one by one they would type it out with their brain. But it's very, very slow. It's about 10 words per minute, and it is not really practical in the current state. So the alternative solution to this is neural speech decoding, that is directly retrieving speech information from the brain so that we can decode the speech information, different speech features, and then synthesize speech. And one basic baby step to do that is synthesize the speech envelope, which basically what the study represents. It's the ideal goal would be to synthesize the entire speech, all features, the entire waveform, audible speech, and that has been done with ECOG. I mean, at least a very preliminary study has showed that yes, we can decode and synthesize speech just using the brain signals. But that was for invasive electrocorticography. That basically they are placing electrodes on the brain and then getting a very high quality brain signals when the subjects are speaking something, and then they're just using the brain signals to train with the corresponding speech as the output. Non-invasively, which is the ideal case to develop any kind of speech-driven brain-computer interface, or the patients, or it could be used by healthy participants as well. The majority of the work only involves classification of few speech units. For example, yes versus no. Can we just use the brain signals to classify whether the patient or the participant is thinking yes or no? And believe me, that is also a very significant contribution, because using just yes or no, we can a completely paralyzed patient, if they can talk to their family, that is also a very significant. However, it's not enough. And ultimately, we would want to synthesize the speech using the non-invasive modality. So previously, some research work has been done to decode the speech envelope of perceived speech. So what we are hearing, if we have the corresponding acoustics, can we decode the envelope of the speech that we have heard using the brain signals. And there has been a tons of research on that. But can we do that when we are speaking, or when we are imagining speaking, or when we are intending to speak? So imagining speaking, meaning without moving any articulators, but speaking it loud, is inner rehearsal. Intending to speak, meaning I'm attempting to speak, or after some time I would speak that, but it's mostly in the planning stage. Whatever I'm speaking, because it's very natural and we have been trained, it's very natural to us, so we don't really understand. But there is a gap, a reaction time, you might say, that takes the speech planning and speech motor command in the brain. If we can use that amount of data where there is no acoustic output, and then understand what the person is attempting to speak, that is called intended speech decoding. So in this study, what we have tried is to decode the speech envelope when subjects are imagining, intending to speak, and overtly speaking. So with the aim of speech envelope synthesis, we are using magnetoencephalography, neuroimaging modality that detects the magnetic fields in the brain corresponding to any postsynaptic neuronal activation. If you have heard about EEG, it collects the electric fields in the brain corresponding to any task. And whenever there is electric field, there will be a corresponding magnetic field as well. So the idea here is with EEG, when we collect the electric signals, it gets distorted when we collect it out of the brain. By out of the brain, I mean outside of the brain, because of the volume conduction effect. I mean, our skull, scalp, etc., there are certain resistance to that. And whenever the current is coming out, any electric field that's coming out, that gets distorted because of the volume conduction. But with magnetic field, when you're measuring the magnetic field, because of the same magnetic permeability, the signal distortion is a little bit less. So in one way, MEG might have a very higher, or like a little bit edge over EEG, and that's why MEG is like the focus of the study. We asked the participant to just pick yes or no randomly. So they would be like yes, yes, no, no, without any cue. By cue, I mean, we are not asking them any question. They would just randomly speak yes or no with their self-paced rate at their own will, at their own choice. Then we also showed 5 different phrases, very commonly used phrases like how are you, do you understand me, goodbye. And they read that sentence from a screen and then they spoke it out loud, imagined it. So the idea here is just use the neural signals, have the speech data, get the envelope, and try to train a regression model that can basically regress the brain to the speech domain. So the feature that we used is basically the band power. For non-neuro folks, there are different type of neural oscillations that have specific characteristics or functionality associated with different type of cognitive action. For example, any kind of information processing in the brain typically happens in very high frequency range that we call gamma. Any kind, like when we are asleep, it's we are in a very low frequency range, starting from alpha to theta to delta. So basically 0.2 to 4 hertz is like the frequency range that different neurons oscillate at that time. So because the speech perception envelope you see here is very such a low frequency wave, traditionally in literature, people have mostly used the delta or delta plus theta, that is under 8 hertz frequency filtering and they have used that as input. However, when we're talking about speech, that is for speech perception, that is auditory speech. But when we're talking about speech production, it typically requires information from the high frequency region. As I said, information processing requires high gamma frequencies. That's why we used both high frequency as well as low frequency for comparison. And we just used a bidirectional long short-term recurrent neural network model, just a simple BLSTM recurrent neural network model. All right, some more things about MEG is it's non-invasive. You can see the machine here. It has very good spatial and temporal resolution. The magnetic field is less distorted. I have spoken about this before. However, the most important thing is recently, this machine that you see here is being converted to a portable MEG with similar signal quality. This is called a optically pumped magnetometers based MEGs. And this is a very hot topic right now in the neuroimaging or the MEG magnetic field community. The idea here is, I I mean, obviously, using this big machine, we cannot really provide, it's very costly, it's not portable, and we cannot use this as a PCI device. However, the essential mechanism is the same. It captures and analyzes the magnetic field in the brain. And this wearable device can do the same. So anything that we have done using EEG, or research projects that we have, any kind of research that we have done using MEG, with this kind of optically pumped magnetometers, we should be able to make it, take it out of the lab and be usable by real users and patients. So it's the future of this kind of device is really high. There are huge potentials, and speech BCI could be one of them. And that is the real motivation of using magnetic fields in this study. All right, so a very just a simple model architecture data distribution that you see here. Very quickly, there are like 7 different subjects. We are doing the decoding for each subject separately. There are 7 different subjects. They spoke yes or no. 7 different subjects spoke 5 different phrases. By trials, I mean number of samples, number of repetitions of those phrases. And you can see it averaged around 65. And for watch, it averaged around 80, like 80 times yes and 80 times no. And sensors is the amount of sensors that is placed around the brain. If you remember this machine, this is called a sensor cap, that there are radiometers, and it measures the changes in magnetic fields in the brain. So it contains about 204 sensors, but after pre-processing, some sensors were noisy and we just removed them. For example, for this data, we just removed 1 sensor, but here you can see for different subjects at different time, there were certain sensors very noisy. So yeah, it's a very high dimensional problem as well. We basically have 200 signals and we want to regress it to a 1-dimensional signal. And that 1-dimensional signal is the speech envelope. These are some basic hyperparameter and architecture details. What I would like you to focus on mostly is like the sampling frequency is 1004 kilohertz. It's not the very high speech frequency range. And the input dimension is basically there are like for phrases, it takes about like 1 second, and for words it takes about 0.3 seconds just to speak yes or no, and we just use that for overt speech, and the corresponding part for imagined speech. For imagined speech, we just use 1 second before the trial. And these are just a simple LSTM architecture using, it required a lot of regularization and hyperparameter tuning, and we did that for each subject separately. All right, so some interesting stuff now. Now here you see the blue line is the ground truth speech envelope, and the orange line is the predicted one. This is for a word no, for a test case. I mean, this is obviously cherry picked. The correlation is about 0.97. And this is for a phrase when the subject is, when the participant is speaking, do you understand me? And you can see the prediction versus the ground truth. Well, it's definitely, they are cherry picked examples. All the trials were not like that, but what I would like you to notice here is a simple LSTM model is able to regress to the speech envelope waveform. And another thing for the phrase that you see is this silent state, right? So 0 is the cue to speak. So here the subject was instructed to speak, and the participant took about 400 milliseconds as reaction time or something, and they spoke the sentence. And here they stop speaking, and after that there is no acoustic output. But neurolinguistically, this is the part where they actually prepare speaking, the speech preparation. And even after they have stopped speaking, after this there are also auditory post-processing that goes on. That also relates to this particular speech. However, for this particular result, as you can see, it not only regressed to the exact speech envelope, however, it also detects the silence very effectively. And this is also very important when designing a brain-computer interface to understand where the onset and offset of the speech is. Now, I have talked a little bit about, I've talked a little bit about how previous research have used just the low frequency information for auditory envelope regression. And you can see here the comparison of that result. Let's focus here first. When we're using just word stimuli, and we are using all the high frequency information, low frequency, everything starting from the low frequency to high frequency information, the correlation score across the 7 different subjects for all the trials is about 0.8. right? 0.81 or something. But when you're using just the low frequency information, just the delta, it decreases a little bit. And when you're using adding more low frequency information, it further decreases a little bit. So the idea here is, word is a shorter speech unit. The time required to speak yes is very less. It's about 0.3 seconds. But when we're using phrases that is 1 second long, there is no significant difference between low frequency or high frequency. And this also explains a very interesting phenomena, that to process, speak, or to do any kind of speech, a longer speech stimuli, it's because of the nature of the duration. The low frequency waveform is very easily, the brainwave will be able to easily understand it because of the duration of the information. For words, because of the shorter length, it's the high frequency information that is being much more crucial, and it is contributing to the decoding performance. But for short phrase, I'm not saying that the high frequency is not contributing. It's definitely contributing, but the low frequency is enough to decode the speech envelope. And every previous research that have used for speech envelope regression, even for acoustic, like auditory perception, they have used very long sentences, starting from 2 minutes even. Sorry, not starting from 2 minutes, starting from a second to 2 to 5 minutes. That's why previous research have very much focused on low frequency information for speech envelope regression. This is also another interesting result. As you can see here, when we are decoding the speech envelope during speech production, this is the average correlation score. When we are using the production envelope as the label, but taking the imagination part as, because during speech imagination task, they would just imagine speaking. There is no audible output. So we are taking the ground truth data from the speech production task as the label for speech imagination task. I'm sorry if it's confusing, but the idea here is because it's the same speech samples in the same trial, and because there is no imagination output, we are taking the speech production output as the ground truth level for the regression model. And it was not very good. It's definitely higher than the chance level. Chance level was about 0.17 based on bootstrapping. And just by using, without any auditory output, if you are using just the speech imagination data, and we are able to synthesize the speech envelope that without any acoustic output, and that is significantly higher than the chance level, it further emphasizes that speech BCIs could be possible. However, the more interesting result is for the word case. When we are comparing the production versus intention, remember, intention is the speech planning part, when the brain is planning to speak, and we are just using that data and a significant amount of other data as well. And you can see it's very, very close to speech production. I mean, there was no significant difference in the performance. This further emphasizes that maybe it's time we move towards speech intention, intended speech-based BCI compared to imagined speech-based BCI. All right, so in conclusion, what we observed is, like, we obtained about 0.82 correlation score for speech envelope synthesis for words and 0.72 for phrases. We definitely observed speech and intention envelope decoding is much more achievable. We also found that significant better performance with wideband oscillation, that is all frequency ranges compared to just low frequency ranges that is proposed in the literature. But we got that only for shorter speech units, not for the longer speech phrases, like 1 second long. And this is just a baby step. We have just been able to synthesize speech envelope. Ideally, what we would like to do is synthesize the exact speech waveform. This is the first foundation towards direct speech synthesis from the non-invasive neural signals. A clear limitation is the vocabulary size. We just used 5 different sentences and their repetitions and some words. Just to understand that our model is not overtraining, we kept one sample completely unseen. So for 5 different phrases, we just trained with 4 phrases and tested with a completely different phrase. Just to understand, yes, it's not just decoding 5 different types of speech, rather it's actually doing the envelope regression. Similarly for yes or no. But ideally, the real validation would be when we increase the data size, which we are collecting now. We are collecting about 400 phrases, the Mukatiman data set, and we are going to repeat the same work along with speech collecting data from ALS patients. All of this work is done on healthy participants, we would like to reproduce that for ALS patients. That is the true challenge of the speech BCI paradigm. So yeah, I would like to thank my advisors and the fundings for this research. I would like to thank Dr. Malik, McManus, Bertis, and Christine for helping in data collection, and the volunteering participants, without which the research wouldn't be possible. And I thank you so much for your attention. And if you have any questions, please feel free to ask me. Thank you so much.
Yeah, thank you very much, Devadatta, for this nice talk. We are obviously burning for your topic, so it's very, very nice to hear. So in which year of your PhD are you? The second?
I'm final year PhD candidate.
Sorry?
So I'm defending in November.
Okay. Yeah, so actually I have a question. So you have presented results on your work, but I was just wondering, I mean, did you test your system on real patients already? This seems to be very, very challenging, because it also includes a lot of ethical issues, and it's certainly not so easy to get a good group of patients that would be ready to participate in this type of studies. Can you say something about this?
Yeah, that's actually a struggle. It's very difficult to collect data from patients, but it's doable. Like I work in the hospital, my advisor work in the hospital. So there are a lot of patients that comes to the hospital, and they are getting referred for research, and they are very happy to contribute. And just to contribute such that, I mean, ALS is kind of a disease. They have a lifespan of 2 to 4 years. They know that it's not, this kind of research is just starting, and within 10 years, we won't be probably able to like give them or provide them a speech BCI. It might take a longer time, but when we explain the intention, they are definitely more than willing to participate in the research. We have collected so far data from 3 ALS participants, and the interesting result, what we have observed so far is there are no difference in intended or imagined speech envelope regression, but there is a significant decrease, completely near to chance level when they are speaking. I mean, it makes sense, but the idea that ultimately we would like to do that for imagined speech, so that's a positive sign, but I'm not yet sure why. It's obvious that they are not able to speak, and the ground truth output is not really good because of the speech envelope is very bad. But that could be a reason. And when we try to use the healthy people's speech envelope using some DWT, dynamic time warping, to find which envelope is more correlated with that particular trial, it still didn't work. So it's definitely there are some the overt speech production of the ALS patients. It's the acoustic output is not clear, and the brain signal is too noisy because of compensation mechanisms. So it's challenging. However, we recently submitted the paper, and the fact that the imagined and intended speech envelope is possible, that could be a positive sign for to focus more on the speech imagination decoding.
Okay, thank you very much. So I don't want to take more time from my side to ask questions, because we have a question from the audience. Tamas has a question. Please go ahead. Yeah.
Yes, thank you very much for this nice presentation. My question is related to the speech envelope figures. So you mentioned that these were cherry-picked examples, and they were really nice, but it would be great to see some bad examples. Like, I don't know, how would a bad example look like? Is it very, very far away from the real speech envelope, or just, I don't know, half of the speech envelope, or can you, because usually from the bad examples, we can learn more what should be improved.
Yeah. So from what I've seen, for example, if you say this, a bad example would be just one, like a wave, sine wave, or just one peak. Or another bad example would be not able to capture this, this dips. So, and that significantly reduces the correlation value. For example, if I remember correctly, the worst correlation performance I got is about 0.2. Like it was still higher than the chance level 0.17, but still, I mean, correlation is not a good measure to really get find the suitable, because we got such high correlation values, 0.8, that from now, I mean, from that result, we can make an argument the RMSE score is definitely below 0.2. I mean, these are trained based on the RMSE scores, the earliest games. So there are definitely some bad examples, but if you see the standard, if you see this is standard errors. The standard deviation would be much low, but probably it would have been better if I showed a box plot. But there are definitely at least 5%, I want to say, examples which are pretty bad, about 0.2 to 0.3 range. But yeah, that's a very interesting question. It's basically, I don't see any changes in the waveform. I just see just a wave, like a sine wave or a cos, something like that. When I those are basically pretty bad.
Okay, thank you very much.
Thank you.
Okay, thank you. Are there more questions from the audience? Audience is increasing, so we have now 11 guests. So, okay, no more. So, seems to be that there are no more questions from the audience. Yeah, so then I think we are just on time. I mean, it's it's 7 o'clock in St. Petersburg, and the session is now supposed to end. So I would like to thank everybody for the good discussions and the nice presentations from the presenters. Yeah, thank you so much. And so I think then we are done. Alexei, you are the big boss. So
thank you, Wolfgang. Indeed, we are perfectly in time. Thanks to you and all the speakers. So that's all for the second day of SPECOM, and see you tomorrow morning at 10 a.m. We continue our SPECOM. Okay. Please join again.
Okay, bye-bye. Thank you very much.
Bye, guys.
Bye.